We're going to review for some midterm material. Units 1 and 2 I'm not going to spend much time on. That's when we did dimensional analysis and like cross-canceling units to convert between one and another. We did some measurement. The big idea behind the measurement is that when you are using a tool that has tick marks, you always estimate 1 digit past what the tick mark represents. So for example, when you have a graduated cylinder, just add some tick marks. Okay. So let's say this is 2 and this is 3. Okay. You want to read at the bottom of the meniscus, and it looks like the bottom of the meniscus is kind of at 2.1, 2.2, 2.3, 2.4, 2.5. It looks like it's kind of right on the money at 2.5, but you want to estimate 1 digit past that, and you call it 2.50 milliliters. So because the tick marks go to the 10th place, like 2.1, 2.2, 2.3, you need to estimate out to the 100th place for this particular graduated cylinder. And then we also did scientific notation. And some of you guys sometimes get weirded out about that when you guys get an answer that's in scientific notation, but it's still just a number. So if you get a number that's like 1.4 times 10 to the negative 7, that means it's a small number, and you're going to move the decimal to the left 7 times. So if this is the decimal right now, you go 1, 2, 3, 4, 5, 6, 7. Plant it, and then you fill in the rest with zeros. So it's 0.000000014. Or if you take a big number, let's say 56202. If you want to take this and put it into scientific notation, it's a big number. So you know that the exponent is going to be positive and not negative. But currently here is your decimal, and you want to move it until only 1 digit is to the left of it. So I'm going to move it here 2, 3, 4, 5, 6 times. Plant it. So my mantissa is 5.62 times 10 to the 6 because I moved the decimal 6 times, and it's a positive 6 because it's a large number. All right, so that's pretty much all I'm going to cover for units 1 and 2. Unit 3 is when we start talking about protons, neutrons, and electrons. There is the history of the atom, of like how we knew that electrons exist, the nucleus exists, and you guys do have to know that. I'm not going to cover that here. You have some notes that lay it out for you, and there's a PowerPoint online. If you scroll back on the calendar, you can find it. The big one, though, is the discovery of the nucleus, that's in the electron. Okay, but in general, your protons and neutrons are located in the nucleus. So that's where you have your positive protons and your neutral neutrons. Those are all in the nucleus, which is super duper small and dense. And then on the outside is where you have your electron cloud. So we really represent that as like dots of electrons of where they're most likely going to be found. So usually I was just trying to show the charges of where they are. But here's the nucleus, super small and dense. And then the electron cloud represents where the electrons are most likely going to be located. So if we were to make a little table of protons, neutrons, and electrons, their location, the protons and neutrons are in the nucleus. You'd say the electrons are in the cloud. And then as far as their mass goes, remember the protons and neutrons are pretty heavy. They're about 1 atomic mass unit each, but the electron is so small. It's like 0.0, I can't remember off the top of my head, but it's super small, much, much smaller than 1 AMU. So electrons are super light, and that's why when we talk about like the estimated mass of an atom, we leave the electron out. So when we built the symbol of an atom, so let's call this sulfur 3316. The 33 represented the mass number. We'll get to what that is in a second. Number 16 represents the atomic number. And then what's not written in the top right corner is the charge. So the atomic number is going to define the fact that this is sulfur. No other element has this atomic number. It's the same thing as the number of protons in the nucleus. That is what defines the element, is the number of protons. Now, the mass number is the estimated mass of that particular atom in AMU. And the mass number is found by taking your protons plus your neutrons. We leave the electrons out, remember, because they're so light that when we gain or lose them, they don't really change the mass of the atom that much. Now, the charge is a balance of how many positive protons you have compared to your negative electrons. So you have to compare those two. Your neutrons are not involved because they're neutral. They don't have a charge. So if the charge is 0, that actually means you have the same number of protons as you do electrons. Okay, so if I were to count how many protons, neutrons, and electrons this particular atom has, the protons is 16. However many neutrons I have, I can figure out by taking my mass number minus my number of protons, right? Because this is your protons and your neutrons added together. If you subtract the mass of your protons, you get just that of your neutrons. So set 33 minus 16 is 17 neutrons. And then if my charge is 0, that means I have the same number of positive protons as I do negative electrons. So I also have 16 electrons. Okay. If I were to compare that to this and this. Let's get some practice of the protons, neutrons, and electrons. If you want, try to stop the video and try it out on your own for a brief second. Go for it. All right, so your proton count is 16 for all of these because that's the atomic number. That tells you that this is sulfur. To get your neutrons, take your mass number, your neutrons and protons, minus your number of protons. So it'd be 16 here and 17 here. All right, your charge is still 0. So that means your pluses and minus are the same in number. Here, though, the charge is -2. So that means it's an anion. It has extra electrons compared to protons. How many more electrons do we have? 2 more. We have 2 more negatives than we do positive protons. So that must mean we have 18 electrons because that's 2 more than 16. Okay, now let's go backwards. I'm just going to give you the neutron, proton, and electron. And we're going to go backwards. And we're going to build a symbol. Okay, so remember the proton count tells you what the element is. So element number 35 is bromine. And to get the mass of this atom, we ignore electrons, they're super light, but we just take our protons plus our neutrons, which adds up to 80 AMU. And then as far as the charge goes, we have 1 more negative than we do positive. So the charge is -1. Or you can just put negative if it's -1. But if it's -2, you have to put -2. Okay, now, so this is an ion, it has a charge, but there are things called isotopes. Isotopes are atoms of the same element that have different mass. So how is that possible? They have the same number of protons, that's what makes them the same element, but they must have a different number of neutrons if they have a different mass. So can you identify any of these that are isotopes? It would be these two, atoms. So they both have 16 protons, but they differ in their number of neutrons. These are really the same isotope. It's just that one is charged and this one's not. Okay, so these two are isotopes of each other. Now, one thing about isotopes is that the average mass of the isotopes make up the mass that you see on the periodic table for that element. So some sulfur atoms weigh 33, some sulfur atoms weigh 32. And there's probably others out there, but these are two major ones. But if you guys look at the periodic table for sulfur, you find its mass to be 32.065. So remember, that is the average atomic mass of sulfur in AMU. And because it's closer to, because it's closer to 32 than it is to 33, that tells us that in a sample of sulfur, we have many more sulfur 32 atoms than sulfur 33. This dominates the sulfur atom mixture. We have more 32s than weigh 33 because the average mass is closer to 32 than it is to 33. So we'd say sulfur 32 is more abundant. It's more common in nature. And we are able to actually calculate an average atomic mass for those elements. So the average atomic mass, I'm just going to use abbreviation, is equal to the mass number. So you would take like 32, for example, times its percent abundance in decimal form. So that means you divide it by 100. And then you take the mass number of the other isotope and multiply it by its percent abundance in decimal form and add them all together. Okay. We'll just do one more unit. Unit 4 is nuclear chem. So what happens when we have reactions inside of the nucleus? The goal is to become more stable. To do that, the isotope, the unstable isotope, releases radiation in the form of particles usually, and energy. Lots and lots of energy, and that's how it becomes more stable. So you always start with an unstable parent isotope, and then it will break down, release some radiation, become the stable daughter, plus some radiation, some particle, plus energy. Okay, so we have 3 different types of radioactive decays of particles that could be emitted. So first we have alpha. That is technically when an unstable parent isotope releases a helium nucleus, or we could rewrite that as 4/2 with the alpha symbol. For example, if you have uranium-240 and it gives off alpha decay, you should be able to figure out what the daughter isotope is. So if you treat the arrow like an equal sign, 4 plus the mass number of the daughter should equal 240. So that means it should be 236. 2 plus the atomic number of the daughter should equal 92. So that should be 90. And then you look at the periodic table for what element 90 is, and that's TH. Alpha is the least energetic, least dangerous on the outside of your body. A beta particle is when a neutron from the nucleus turns into a proton and emits a beta particle, which is an electron, in the process. And the electron comes zooming out of the nucleus, but the proton stays behind. It's wild, yes. But essentially the electron that comes flying out of the nucleus is the beta particle. Remember, electrons don't have a mass number, and you consider their like atomic number to be -1. You can also replace the E with the beta symbol. So an example of that would be carbon-14 undergoing alpha decay. I'm sorry, beta decay. And figuring out what the daughter isotope might be. So 0 plus what equals 14? You would say 14. -1 plus what equals 6? Think carefully. It's not 5, it's 7. And look at element number 7 on the periodic table. That would be nitrogen. The last and most dangerous form of radioactive decay is gamma. It's pure energy, so that's why it's 0, 0, gamma. That will not change the parent versus daughter. It'll just make the daughter more stable because it's losing energy. Now, how quickly this radiation happens differs on the element. And that is what we can predict using half-life, how long it takes. So think about what half-life means. It's the amount of time it takes for half of the atoms that are radioactive to decay. So for example, let's say we have a half-life of 7 days, like a week. For this particular substance, we start with 100 radioactive atoms that are parent isotopes. How many are left after 21 days? Okay, so half-life, 7 days. Every 7 days, half of the atoms will decay. But we have more than 7 days go by. We have 21 days. So if we count how many half-lives that is, that'd be a total of 3 half-lives that occurred. So start with your 100 atoms and take it through a series of 3 half-lives. So over the first half-life, half of the atoms will decay and we'll be down to 50. Then the second half-life passes by and we're down to 25 atoms. And then the third half-life occurs and we're down to about somewhere between 12 and 13 atoms that are going to be left that are radioactive. The other 87.5 are now the stable isotope. So this is how many are still radioactive. The other 87.5 are the stable. So the half-life is my arrows. Every arrow represents a half-life in the way that I set up these problems. Okay, that is all I'm going to go over with you today. Hopefully on Monday, or if we get done with the test early tomorrow on Friday, we can start electron configurations, because I think a lot of us forgot how to do that. Periodicity as well, and your favorite naming compounds. But keep working on that midterm review packet. Remember, the key is posted on Monday before review on the calendar of assignment and keys on Schoology.